The highest mountain peak in the world is Mount Everest, located in the Himalayas. The height of this enormous mountain was determined in 1856 by surveyors using trigonometry long before it was first climbed in 1953. This difficult measurement had to be done from a great distance at an altitude of 14,545 feet on a different mountain. The straight line distance to the peak of Mount Everest is 27.0134 miles, and its angle of elevation is 5.82 degrees. Okay, so with this, let's approximate the height of Mount Everest. Okay, now, personally, if I was taking trigonometry, I would be wondering, well, how would you know this length? How could you know this length but not know the height? Well, I'm not an expert in surveying, but my guess is this is similar to a problem we worked previously determining the diameter of the sun, and where we had the distance, the straight line distance to the sun. But in that problem, I think it was pretty clear that if you could get the included angle of the edges of the sun, then you would have an isosceles triangle, and you could use just regular geometry, not right triangle trigonometry, to find like the straight line distance to the sun, the diameter of the sun, etc. But they were just using that for that problem, giving us the straight line distance for illustration of applied trigonometry. And so to me, this is a similar situation in that these surveying devices can find or are great at finding angles between features. So you can have like far off features like a mountain tip peak, and you could find like the surveying device could give you this angle of elevation. And so from there you use trigonometry or just regular geometry, some combination of those, to get distances that are hard or impossible to measure. So what I imagine is, they can climb to the heights like this so they can get views of like the peak. And so they know the height they climbed, and then they could get some angles relative to the peak and then use geometry relations to get this height and then add that to this height to get the elevation. But since we're studying trigonometry and they want to give us an example, let's imagine that they used regular geometry and some other method to get this distance, right? So now they used regular geometry with angles to get this distance. So now with this distance, can we go ahead and calculate the height of Mount Everest? Yes. So what we're going to do is, we'll call this is H, and the height of Mount Everest is H plus 14,545. So what we need to do is we need to say that, so this theta is 5.82 degrees. So we're going to say that the sine of 5.82 degrees is equal to opposite over hypotenuse. So the H is equal to, we've got sine of 5.82 times 27.0134. Okay, there's the H. And let's go ahead and, let's just write this out. We're not focusing on significant digits. So, we would typically, I guess, track these precisions and then round to the, get the correct precision. Like we don't want to put an over precise answer, but we're not thinking about that. So let's just go ahead and we'll just say this is 2.74 miles. Okay. Now, H plus this is the height, but okay, so they want the height in feet, so we need to convert this to feet. So how many feet are in a mile? You could do a Google search to get that. 1 mile is 5,280 feet. Okay. So we want to multiply this times Okay, now, and there's the height relative to the observer. So we add to that 14,545. So we'll round that to 29,000. So about 29,000 feet. So this is about 29,000 feet. And just to see what that is in miles, we could divide that by 2.7. Or no. We would do, so that's in feet. So then we say there's 5,280 feet per mile. So we divide that by 5,280. So like 5.5 miles. Okay, in the actual measurement, Mount Everest was over 100 miles away, and the curvature of Earth had to be taken into account. Would the curvature of Earth make the peak appear taller or shorter than it actually is? So I guess this is just like they're just giving us a kind of a fictional example or something. I don't know what they're saying. In the actual measurement, I guess this was like 100 miles. And so how could we answer this question? Well, we could draw like an exaggerated diagram here just to give an answer. So you could imagine that if like this is the smaller mountain and then this is Mount Everest, right? We could exaggerate it even more just to answer the question. Then so here's this distance. Okay, now if you well, okay, I guess what they're probably asking is, because that would be like symmetrical. There, we could think about, so here's the smaller mountain peak, and then Mount Everest is like, something like that, I guess. And if you leveled this out, if you made this level, it would shorten this distance. Right? You can imagine lifting this up, and it would shorten the distance. So the curvature of the Earth makes this distance longer. And what does that mean? That means so this distance is bigger, and so that makes the resulting h bigger. So it makes Mount Everest look taller than it actually is. The curvature of the Earth would. Or wait, no, I'm saying that wrong. Well, maybe I don't know if that's right or wrong, because obviously, if you really exaggerate this, I mean, if you went all the way out to this side of the Earth, then it looks like the peak is below you. So yeah, I guess it would make it appear shorter. Yeah, because as you go around the Earth, it's coming down. It's like, the horizon. It's like making things seem shorter. But I wonder if, it would make this line longer, right? So I don't know. That's an interesting question.